Hello, physics students. In this one, we're going to talk about scientific inquiry and what is not scientific inquiry. So we'll do all of those things in the objectives. And then these are the assessment questions that we'll address when we finish up. All right, here's the physics terms that we'll discuss in this lesson. All right, so science, as defined by the National Academy of the Sciences, is the use of evidence to construct testable explanations and predictions of natural phenomena, as well as the knowledge generated through this process. And modern science, modern society, we have a vast and ever-increasing body of knowledge about the natural world, and we describe this knowledge through models. There can be physical models like your solar system model, mathematical models like an equation that describes gravity, and conceptual models where we use some kind of concept like a gravitational field to explain concepts like gravity. All right, so science is flexible, can be constantly tested and revised and changed, and as we go through scientific understanding of things, you look back at history and realize that a lot of the great scientific discoveries were not widely accepted at the time of their discovery, and scientists had to prove through experimentation the validity of their theories. All right, so limitations though. Science is limited to study physical, testable, observable things, and natural explanations of phenomena. So there are certain areas where science doesn't apply. All right, so there's both a process to physics and science in general, as well as a body of knowledge. So you can look at the diagram here, and that does a nice job of kind of showing you some contrast of those things. So knowledge includes facts and theories and formulas and natural laws, whereas there's also a skill set that goes along with physics where we analyze and we model and use mathematics and problem solving and scientific inquiry to answer questions. All right, so scientific inquiry is a process of proposing and testing explanations to discover which ones are true, or at least test true with the experiments that we design. And one example of that is to discover the law of reflection. You might shine light into a mirror with a certain angle and then measure the reflected angle, and you would discover the law of reflection if you were to do that, because you would see that the reflected angle is always the same as the incident angle. All right, so hypothesis is a tentative, means it could be right or wrong, testable explanation for an observable physical phenomena. And it's not uncommon for hypotheses to be incorrect or incomplete. Hypotheses are still important though, because you can test them and revise them. All right, and then a theory is going to be comprehensive and more well established. All right, so we'll talk about hypotheses versus theories. So Newton hypothesized that light is kind of like a particle and it bounces off of a surface. Others proposed that it behaved like a wave. And then kind of ended up being that neither model was completely correct. Both light has, in certain experiments, behaves as a particle, and in other experiments behaves as a wave. All right, in everyday language you might use the word theory, like my theory about this is that, and fill in the blank. And that's more like a hunch. So a scientific theory is going to have been tested and criticized, and the findings of that theory will have a degree of repeatability. Right, so the scientific method is the process for proposing theories and then testing them. And you're only going to have a hypothesis become a theory if the outcome of every related experiment or observation agrees with the hypothesis. All right, so here's a flowchart showing the scientific method and how it relates to the Earth is flat. So you could start out with a question. What is the shape of the Earth? You have a hypothesis. Let's go with the flat. So if the Earth is flat, you travel in a ship in one direction. You will fall off the Earth's edge. Well, you test it, and then you end up returning to your starting point. Kind of think about the voyage of Magellan making it all the way around the world. So you end up back to the starting place, and you're like, well, that contradicts my predictions, so let's go revise this hypothesis again, and maybe we go for a more spherical hypothesis the next time and see if our conclusion matches. All right, so these adjectives, whether they describe theories, hypotheses, or both, maybe take a moment, pause the video, and then I'll come back. Yep. And then here are the answers. All right, so scientists do have an impact on society, and the work of each scientist is built on the results of others, and let's look at some examples of that. So the Big Bang proposed, and then somebody did some math to predict the universe's temperature based on the theory, and then somebody else predicted the temperature, and then somebody else, verified with an experiment, and then mapped the background radiation and tried to relate that to modern day clusters of galaxies. And the scientific theories, they're always subject to change as new areas and new technologies are developed. All right. Another place where you can see some relationships that might not immediately be obvious, but so geological teams noticed lots of iridium in rock from the time of the dinosaur extinctions, and then related that to an astrophysics kind of thing where iridium is present in large quantities in asteroids. So the theory comes about that dinosaur extinction was caused by an impact from a giant asteroid. And then climate change. So scientists are studying the global climate, noticing increase in temperature, and then that's led to discussions about ways to, or how we're impacting the Earth's climate, and what kind of ways to go about mitigating that impact without negatively harming ourselves in the process. All right, so let's see, tools for analysis. So we're going to talk about observational evidence, logical reasoning, and experimental testing. So you can make observations, and if you observe Venus for an extended period of time, those observations would fit the model that the Earth and Venus both orbit the Sun. It's very hard to explain without assuming that. And these observations are objective and repeatable, so they do fall in the category of scientific evidence. All right, so another example, so logical reasoning. If you're trying to explain the Earth's seasons and because of the fact that the Earth's rotational axis is tilted, so it would follow logically from that if you are observing at a location that's 30 degrees north latitude, then a little bit of math would reveal that in the summertime the sun should be 7 degrees from vertical. In the wintertime it should be 53 degrees from vertical, and that's what you observe. So that is objective and repeatable every year. All right, experimental testing as well will give you objective and repeatable information, and that would be gathered through completing an experimental investigation. All right, so if you're critiquing the experiment, is it objective? Are the observations unbiased? In other words, did you want a certain outcome from this experiment, and perhaps could you have modified or altered the data in some way? Could other variables have caused the observed effects? That's why it's important to control the constants within the experiment and also have a control group. And then do other researchers have the same result? If you get a great result from an experiment, then your work should be published, and then others should repeat the experiment. And also you should analyze the data and understand the uncertainties in measurement. And if the uncertainties are greater than the observed effects, such as an experiment a few years back where I think it was some neutrinos were thought to go faster than the speed of light, they ended up figuring out that the uncertainty in the measurements was greater than the amount by which those neutrinos were going above the speed of light, so the results from the experiment were not valid. All right, so there is a certain amount of uncertainty in all measurements, and it's a matter of the amount of uncertainty that's present. So if your uncertainty is much less than the observed change, then you can be reasonably confident or very confident that what you're observing is indeed a result of your experimental changes. So here's an example. So perhaps your thought is that heavy objects fall faster than light objects. So you do this experiment multiple times where you drop a heavy rock and a light rock at the same time, and you notice that they take the average, and the heavier rock has a slightly lower time to reach the ground than the lighter rock. And he says, yeah, this data supports my explanation. His friend says he's wrong. What is the evidence for each view and who's right? Well, let's take a look at the data here. The times seem to vary pretty wildly between 0.67 and 0.93, and then these times vary between 0.65 and 0.98. So the uncertainty here seems to be in the tenths place, because they don't get a repeatable result in the 100ths place at all. There's variation, 0.6 to 0.9, same thing here. So it doesn't seem that the times being taken here are with precise out to the hundredths place. All right, I'll finish these notes up in the next video.